Hummingbirds are very unique creatures and are the only bird that is able to hover and fly backwards. They are able to do this through the amazing speed at which they beat their wings and the manner in which they move their wings to fly. Hummingbirds beat their wings up to 80 times per second and move their wings in a figure 8 motion rather than up and down in order to generate lift on both the upstroke and downstroke. This is what gives them the ability to hover and keep their body still while flying. Hummingbirds use this skill to stay stationary in the air while drinking nectar from flowers. We can model the hummingbird feeding from a flower as a continuous, controlled, dynamic process. First, we will define our frames of reference. We are going to set the center of the flower as the origin of the inertial reference frame, with the axes A, B, and C. We will then create another reference frame with the origin at the center of mass of the hummingbird and the axes X, Y, and Z. This frame will move relative to the flower's inertial reference frame with the angular velocity omega. The magnitude and direction of this movement is controlled by the speed and angle at which the hummingbird beats its wings and the way it positions and moves its body up or down and side to side. When the hummingbird is drinking from a flower, the Y and B axes would be lined up and omega would be 0.
The main forces acting on the hummingbird are the force of gravity and the lift created by the beating of the wings. There is also a moment created by the movement of the hummingbird's tail feathers, which act like a rudder to keep the hummingbird steady while drinking from the flower. In order for the hummingbird to drink from the flower easily, it has to be in a state of equilibrium, meaning the force of gravity must equal the force of lift, and the sum of the moments must equal 0. The hummingbird's motion is a very complicated dynamic system that has far too many variables for us to model it completely accurately. For this reason, we have simplified the motion of the hummingbird to be confined to translational movement or rotation about the z-axis. When the hummingbird is drinking, it must have no translational movement and no rotational motion.
The force of gravity is simple and will depend only on the mass of the bird and the acceleration due to gravity. Lift is more complicated and is dependent on how fast and in what direction the hummingbird beats its wings. We will use the angles A and B to define the positioning of the wings, with the rate of change of those angles determined by the frequency. The movement of the tail feathers also affects lift and controls the rotation of the bird about the z-axis. We will define the angle of the tail feathers with respect to the xy plane as theta and the angle with respect to the yz plane as delta. Therefore, the function of lift is dependent on the frequency of flapping, the angles A, B, and theta, and the coefficient of lift of the hummingbird's wings. The moment about the z-axis is a function of the angle delta. Here, a hummingbird was placed in a wind tunnel and filmed with a slow-motion camera. You can see the way it beats its wings and positions its body and tail feathers in order to drink the nectar from the artificial flower. The hummingbird is able to keep its head almost perfectly stationary while it drinks the nectar, which takes an extraordinary amount of control.
Using the functions we derived earlier and the position of the bird, we can define our state vector, which would be the input to our system. Once we have that, we can take the derivative of the state vector, rearrange it into state space form, and evaluate the state at which we would find equilibrium. After we linearize the state space, we can use the built-in MATLAB function SS_TF to transform our state space equation into a transfer function that we will use to model the system with Simulink. We can develop a schematic block diagram of the process to evaluate how the hummingbird approaches equilibrium. The block diagram will consist of a sum block, which will add the response from a PID controller, a transfer function block, of which the numerators and denominators were provided by the SS_TF MATLAB function, and the feedback loop, which returns the sum block. The output is the new state for every parameter of the state vector at every time step, and each input has its own unique output. Based on observations on how they approach a flower, and how they correct themselves once reaching it, we can say that it is most important that fast settling times with minimum overshoot are more important, instead of how quickly it rises to a fraction of the steady state altitude. The approach must be controlled as to avoid excessive oscillation about the equilibrium point, which means that the derivative gain in the PID controller plays a larger role in how the hummingbird corrects its motion to stay at equilibrium.